So we were studying about the magnetic effects of electric current. Na? So tell me about the magnetic field around a straight conductor. Magnetic field around a straight conductor. Concentric circles. Then what and all we have? So next one after that. Next. What we know more about that? In that?
Inversely proportional to the distance.
Magnetic field is inversely proportional to the distance from where? Distance from the conductor. From the conductor, if you go far, it is. Then what else we studied in the 2 or 3 points are there. No, I'll ask some other questions also there. I'll ask. Don't worry.
And if you do many rows.
That is different. Just I'm asking, in a straight conductor, magnetic field is produced when current is passed through that. So about that, you tell me about that.
It's directly proportional to the current.
It is directly proportional to the current and inversely proportional to the distance from the conductor. And magnetic field direction changes if the current direction changes. Tejasri, which rule we use to find the direction of the magnetic field?
Maximum's right hand rule.
Explain that. Or state that. State that.
If you hold the current carrying conductor in the grip of your palm, such a way that the thumb the thumb indicates the direction of the current, and the curls indicate the direction of
magnetic field. Curls of the finger indicates the direction of the magnetic field. Then we studied about the current in a circular loop. Correct? When current is passed in a circular loop, so about the magnetic field will be produced. Raga, can you tell about that?
Center, it is straight. It is in a straight line.
Magnetic field lines are parallel. At the center, it will be parallel. Then at the edges, they are in concentric circles. Then what else we studied, Netra?
It becomes larger.
Wait.
It's directly proportional to the current.
Correct. Then why it is directly proportional to number of turns? Turns increases, magnetic field increases. The reason is the magnetic field produced in every turn is in the same direction, so they add up. Because direction of the current in every turn is the same, and hence the magnetic field produced is also in this. They are in the same direction in all the turns, so they add up. That is, number of turns or magnetic field is directly proportional to number of turns. Additive in nature. Okay. Then sit here. No, sit here. Otherwise, you will be talking. You should not talk. At the center of the lobes, it will be of parallel lines, and it is inversely proportional to distance from the conductor. It is always the same. Then what else we studied? Solenoid. Kiara, what is a solenoid? So, a soft iron rod, when it is placed inside a solenoid and current is passed through that, then soft iron rod acts like a magnet. So that we call it as an electromagnet. Whenever current is passed through the solenoid, it acts like a magnet. When there is no current through the solenoid, then it is like a just iron rod. Okay, so that we call it as electromagnet. Electromagnet means whenever current is passed through that, it behaves like a magnet. It has different properties. Mainly magnetic properties of them are different. That's why we use subdiagram. Okay. So there, when how the magnetic properties can be improved in that is mainly the orientation of the electrons will change. Okay, when until the current is passed through that orientation, all will be electrons orientation will be in the same direction, so they behave like a magnet. Okay. So we studied about the electromagnet. Next, last topic, very important topic. Next, whatever is there, it's important. From solenoid, it's very important. Okay, many things we will get now. Force on a current carrying conductor in a magnetic field. Force on a current carrying conductor in a magnetic field. Write down this list. Force on a current carrying conductor in a magnetic field. So Diksha, already you came late. How much you are talking? Huh? Force on a current carrying conductor in a magnetic field. For example, if there is an horseshoe magnet, diagram you can see that in the book and you can write same thing only, but they would have written easily. That's it. What doubt? Just see that. Connected with a battery or a this one. That's all. Here we can take it. Some hands, I think. So, force on a current carrying conductor in a magnetic field. That is, when a current carrying conductor is kept under the magnetic field. Here, this is an horseshoe magnet, which is a permanent magnet. Okay. So, a magnetic field will be produced around it. And when a current carrying conductor is kept under this magnetic field, so a force being applied on the conductor. Again, I repeat, here we have considered an horseshoe magnet, which is a permanent magnet which produces the magnetic field. So, a current carrying conductor is placed in the magnetic field. A current carrying conductor is placed in a magnetic field. Then it experiences a force. So, why the force is being experienced by the conductor? Because the horseshoe magnet will have the magnetic field, right? And the current carrying conductor will also produce a magnetic field. Again, I repeat, see the horseshoe magnet here, what we have used, it has a magnetic field around it, and the current carrying conductor will also produce a magnetic field. So, there are two magnetic fields. Okay, the two magnetic fields experienced by the conductor. So whenever there is two magnetic field, what happens? Either if it is both may have the same poles, then what happens? They attract each other. Or when they are one pole is north and the other is south. If it is like that, they repel each other. In both the cases, the force will be 1 minute. Wait. First understand, then talk. Okay. So it will be experienced. Some force will be experienced by the conductor. Uh, Either the attractive force or the repulsive force. That is by the direction. You have to know that another rule is that Fleming's left hand rule. By that, we will know in which direction force is applied. Again, I repeat, see, horseshoe magnet will produce a magnetic field. Okay. Current carrying conductor, any current carrying conductor will also produces the magnetic field around it. So there are two magnetic fields here. So either if it is like in the same direction, that is both the north pole, if it is facing, then there, it will repel. Correct? If it is one north pole and one south pole, it will attract. So either there will be some attractive force or the repulsive force. So because of that, the conductor will experience some force. Okay, the conductor will experience some force. What you were asking?
You said that and like poles attract and unlike poles repel. And like in the solid order.
Okay. Anyway, you know, no? Oh. Understood now. So there will be either attractive force or the repulsive force that will be experienced by the conductor. So therefore, whenever a current carrying conductor is kept in a magnetic field, it will experience some force. And the direction we know by the Fleming's left hand rule. And here also, what and all we can observe when the current pass through that. When the current pass through the conductor, if it is increased, then what happens? Magnetic field also will increase. So the force exerted on the conductor will increase. Okay. The other way, if the magnet has more magnetic field, if you keep the other magnet which has more magnetic field, then also the force experienced by the conductor will increase. Okay. And if you change the direction of the current in the conductor, then the direction of the magnetic field will change. There, the direction of the force will change. Okay. So what and all we observe here? First thing, when current pass through the conductor is increased, then the force on the conductor will also increase because magnetic field is increased, force also will increase. First thing. Second one, when the direction of the current changes, then what happens? The magnetic field around it will change. So there also it will experience the force, but in the different direction. Okay. Write down few things. So they ask about this also, force, explain about the force on a current carrying conductor. So just write the rough diagram where there is some magnet here and a conductor is kept inside there and current is passed through this. Okay. So just to explain that, we will write the thing diagram. Write down. When a current carrying conductor is placed in a magnetic field, it is placed in a magnetic field, it experiences a force. The force acting on a current carrying conductor, in a magnetic field, is due to interaction between magnetic field produced by the current carrying conductor by the current carrying conductor and external magnetic field magnetic field placed is due to interaction between the magnetic field produced by the current carrying conductor and external magnetic field in which conductor is placed. Conductor is placed. It's fine, no problem. You can write. In which conductor is placed. So, in which direction force been applied, we will know by Fleming's left hand rule. We'll study next. We'll write few things here and then. So, when a current carrying conductor is kept in a magnetic field, what happens? There will be two magnetic fields around the conductor. One due to the permanent magnet and the other one due to the magnetic field produced by the conductor. Since whenever you have the two magnetic field, either there will be the repulsion or there will be the attractive force acting on the conductor. Because of that, a force will be experienced by the conductor. Okay, force will be experienced by the conductor. So there, to increase the force, what and all we can do, either we can increase the current or increase the magnetic field. That is the magnetic field of the permanent magnet. Okay, that can be done. Next, how to change the direction of the force, either by changing the direction of the current or by changing the magnet, that is the direction of the magnet. So instead of keeping like this, if you keep think if it is north and south, if I interchange that to south and north, that is change the direction of the magnetic field of the permanent magnet, then what happens? There also we see that the direction of the force will change. Okay, direction of the force will change. Magnet. Next, we will study about Fleming's left hand rule, where we will be able to find the direction of the force. Fleming's left hand rule. And here and all, see, we cannot see the direction directly, right? Either by that experiment, we will be able to know that, or by the sum rule, we will be able to know. So, by the Fleming's left hand rule, we will be able to know the direction of the force on the conductor. Okay, so left hand thumb rule will indicate we have to use the left hand to know the direction of the force. Okay, we'll write about that. Okay, Fleming's left hand rule. Write down Fleming's left hand rule. Left hand rule. The direction of the current force, write down this, the direction of the force which acts on a current carrying conductor and a current carrying conductor placed in a magnetic field, placed in a magnetic field is given by Fleming's left hand rule, by left hand rule. Okay, it states that the forefinger, thumb, and middle finger of left hand are stretched perpendicular to each other. Stretched mutually perpendicular to each other, such that the forefinger points along the direction of external magnetic field. Forefinger will indicate the external magnetic field. Middle finger indicates the direction of the current. I'll write here the direction of current. Still is there. We'll write. Right. So the direction of the force which acts on the current carrying conductor we can know by Fleming's left hand rule. That means we are using the left hand to find the direction of the force. And forefinger, thumb and the middle finger, all the three we keep mutually perpendicular to each other, where the external magnetic field is indicated by the forefinger. Middle finger will indicate the current through the conductor. Then the thumb finger will indicate the direction of the current. Then listen once here. When we are considering the Fleming's left hand rule, it will indicate the direction of the force. So when you keep the thumb, forefinger and the middle finger mutually perpendicular to each other, that is they are at 90 degrees to each other, the forefinger direction will indicate the direction of the magnetic field. The middle finger will indicate the direction of the current. You keep such a way that they indicate the direction of the current. Then thumb indicates the direction of the force on the conductor. Then the thumb will indicate the direction of the force on the conductor. Why we always keep mutually perpendicular to each other means the force acting on the conductor will be maximum when magnetic field and electric current are perpendicular to each other. Again, I repeat, when magnetic field direction and the current direction are perpendicular to each other, the force on the conductor will be maximum. Always like that, the force on the conductor is maximum. Then what happens when magnetic field and electric field are parallel to each other? Then the force acting on that is very minimum or zero. You can consider it as zero. Again, I repeat, why we consider mutually perpendicular to each other? Because magnetic field and the current direction, if it is 90 degree to each other, then the force acting on that will be maximum. Okay, and when they are parallel to each other, we can say that it is very minimum or zero. Force acting on that will be almost the zero. Okay, so where we use this? This okay, but this phenomenon where we will use?
It's not perfect.
That you have actually formula also is there, but that it will come in 11th and 12th. But you can study.
What if it comes in?
They will not ask, don't worry. What is there only, not everyone will be reading. What you will read after. That is there. That with the cos and sine you will get the thing formulas where with the angle if it is at 60 degree what happens, if it is 0 degree 90 degree, like that. Okay, so according to that the formula you can write what is the magnetic field. 12th, I think you have that whole magnetic field, electric field, and so many things. In what else is there? Alternating current is there in the alternating current and home circuit. That's all. No? What else? Motor is there in the no, not that. In this diagram is there motor thing in your textbook. Just show us. Only that. Some portion they will remove. Alternating current also not there. Okay. Okay. Be quiet. Now this is done. We'll study once about the alternating current. Write down this. Alternating current. In our like to the house, we get the current, right? Whether it's a direct current or alternating current. Alternating current we will get. See, there are two types of the current. One is the alternating current. The other one is the direct current. Okay. So alternating current means it changes its direction. It is like this. Alternating current means it will be changing its direction. Once positive cycle, listen this. Alternating current means it will change its direction. Once in the positive direction, this is called as the positive cycle. Okay. This is the negative cycle. Okay. So once in this direction, next year the direction will change. So when alternating current means continuously it's changes its direction, then we call it as alternating current. Okay, continuously it will changes its direction, then we call it as an alternating current. In an alternating current, the one complete cycle is this. One complete cycle, we call this as a one complete cycle. Okay, so the current what we get to the home, it is of 50 hertz. Listen, everyone here. Whatever the current we get, it's 50 hertz. 50 hertz means this is one cycle. Okay, like this, 50 cycles it will move 50 cycles per second. Then it is called as 50 hertz. Again, I repeat, see, this is one positive cycle, this is the negative. Together, it forms one complete cycle. Okay. So here, once in this direction, then it changes its direction here. Okay. So this is called as alternating current. Alternating current means it changes its direction. Then we call it as alternating current. These questions will come. Okay. What is the frequency? What is the frequency we use in the home is 50 hertz. That is whatever current we get from the power station to here, that has a frequency of 50 hertz. That is for every second, like this 50 cycles it will come. That is one point if you take. Okay, how many cycles will pass through this for 1 second means 50 times. So that's why we call it as 50 hertz. Again, I repeat, like this one complete cycle. This is one complete cycle. Like this in 1 second. How many cycles will pass through that point means 50 cycles will pass through that in 1 second. In our house, what we get is 50 hertz.
Doesn't vary at all.
Maybe that we call it as fluctuation, no? Small fluctuations, it can be there. Maybe very less, 5 per, actually here it will not change much. Maybe 1% here and there, that's it. Not much difference will be there.
We usually measure sound, like if it's just 40 hertz, why do we measure like with hertz?
Many electrical signals we measure like this only because they are alternating in nature, that's why. Every frequency, the SI unit of frequency is hertz, not the sound. Frequency, it is hertz. Frequency means frequency means, see, direct current means it is moving in the same direction like this. Okay. Alternating current means it is once moving in this direction, then it changes its direction. It is produced like that only. That's why. See, what is the reason we use that means alternating current when it is transmitted from power station to here. Here we can produce the power. It is produced in the power stations. Okay, from here there to here, when it is transmitting, there will be lot of losses. If you use direct current, then the heat loss, frictional loss will be very much high. Okay, why means there are so many reasons are there. You should open the book and start reading, then you will understand. Okay, there not given. Okay, that is why we use the alternating current to reduce the losses. Still, even though we are using the from 20 to 40% of losses will be there. Think of using the direct current, then the losses will be still more. To reduce that loss, we use the direct, instead of direct current, we use alternating current. And for many appliances, what we do inside this only, from alternating current, it is converted to direct current and it is used. Okay. That is less when compared to getting the direct current directly. Directly means from wire to here. If power station directly, if you are using the direct current, the loss. Huh? That's what it moves in the same direction. Huh. So frequency means how many cycles it will happen in 1 second. So in the what we get 50 hertz, the complete one cycle like this. From any point, if you consider how many cycles it will pass through, like that means in 1 second, 50 cycles will pass through that. So that's why we call it as 50 hertz. Why it will not make sense?
So he's a traveler longer distance. That means the distance will also be more, right?
It's not like that.
It's not meaning this longer or this longer. This
No, they will produce more heat. So many other things will be there. It will produce, the losses will be more in the direct current. That's why only they use the alternating current. And in power stations, whatever the current produced is only alternating current. Okay.
Why not direct?
That's what, no, losses will be more. To produce that, it is difficult. So many things will be there. That is the reason. Both they used to use only wire only. And you know what is the mobile frequency they use? What is the frequency they use? In gigahertz. Gigahertz means it is 10 to the power of 9 hertz. That means in 1 second, what is how many cycles it will pass through that is 10 to the power of 9 cycles will pass through that from any point. So the frequency of the signals, what we use in mobile, it is 10 to the power of 9 hertz. That is the gigahertz. Okay, that is why, and whenever the frequency is more, the energy in that is also more. That is the reason they say, no, like too much you have to not use. What is the reason is the energy in that will be more, radiations will be more, it may cause the problem like that. So many things are there. I think first you digest this. Radiation means if it is passing through the air, that they call it as radiation. Okay, understood, no? So, okay, tomorrow we will study about the home circuit ones. Can you tell home circuit what type of circuit we use, series or parallel? parallel circuit we use there, because if in a parallel circuit, if one device is not working also, the whole circuit will work, but in series it doesn't not happen. Parallel circuit, not series.
Here we will end the today's class. Do not forget to subscribe the channel. If the content of this channel is useful, please like the video and share with your friends. Thank you.